some of the fish up in the Kimberley using Otolith geochemistry. So I won't bore you with the project because you all know about that. I'll just explain why we're using Otolith geochemistry, and the reason for that is that it's become a really popular technique in fishery science, but it's not really been used in the Kimberley, so we thought we'd give it a go. And my project, because of that, is pretty much a proof of concept study just to see if Otolith geochemistry is actually informative for understanding niche separation and connectivity in these fish. There has been genetics work done in this connectivity part of the Kimberley project. So I'm also going to be comparing my results, if I've got anything that's worth comparing, to these genetic results to see how they compare and contrast, and whether one is better than the other, or whether having the combination is kind of greater than the sum of its parts. I don't know how many of you are fish people, so just to explain what otoliths are, they are found in the heads of fish, and they grow with the fish. And this is really useful because you get calcium carbonate growing on the outside of this thing, which then you can forms rings which you can age like you do with tree rings. But we also get elements from the environment being incorporated at the same time. And if you measure those elements and isotopes, then you can infer stuff about the environment of the animal at that point in time. And because the chemistry will vary from location to location based on the geology of the sort of land nearby, then hopefully you can track movement around using these chemicals. So I'm working with the Janus carpentatus and Pomocentris milleri, partly because these are quite abundant popular species in the Kimberley, and also, as I say, we've got genetics work for all of them. All my samples were collected before I started, so I've got my otoliths all ready to go, which obviously saves a lot of time for me. So I only started a year ago, but I've got results, which is pretty cool. We've pretty much got on about sort of habitat use, and it's just the fact that at different life stages we get different habitat use by the animals, and so I'm hoping that I can pick that up in my chemistry. And what I mean by connectivity in my context is the fact that we know these fish are found all along the coast, but we don't know how that population is structured. Is it one gigantic population of everybody moving around willy-nilly? Is it that every little bay and inlet is a completely separate population, very xenophobic, and no one wants to sort of go outside? Or do we have something akin to countries where you've got a bit of movement at the margins, but essentially everybody sort of stays at home? And again, we're hoping that this can be detected through the chemistry. To do this, I need otoliths. I've got quite a few for Janus. I've got over 700 fish sampled on quite a wide geographic area. So at the moment, my sampling strategy has been to try and get as much of that geographical variation incorporated into my data, which has obviously resulted in a lower sample size per site. So that's obviously the next thing to work on. With the Pomocentris milleri, we had a couple of snags. The first was that we didn't actually have as many fish or as many sites as we thought we did when we first started out. And then the second snag was that while all the fish from the south are adults with manageably sized otoliths, the ones in the north all turned out to be juveniles, and their otoliths are around the size of sort of 5 millimeters and smaller, and they need a very different preparation method, which I'm still in the process of working out. So all my data to date is from this southern end. I'm using 3 different methods of geochemical analysis to work out what's going on. First is a pretty standard technique for otolith geochemistry. This is using trace elements. This is just you section the otolith through the core, and then you do laser spots from the core out to the margin, do a series of spots, and it basically ablates or sort of vaporizes the otolith, and then you can measure the trace elements in that sample, and then you get a nice little transect which will hopefully give you a life history of the fish in the trace elements. And again, these vary from habitat to habitat, hopefully, and so we can infer a lot of stuff from those. The next 2 methods are essentially measuring the same thing, but by proxies. So we're looking at salinity, but you can't measure directly salinity through otoliths. So we look at isotope proxies, and we're looking at oxygen and strontium. Strontium is measured in pretty much the same way as the trace elements. It's pretty much the same machine, actually, and very much the same method. But the next method, oops, wrong way. Oh yeah, that is right. The next method is a little bit more cutting edge. It's actually not really been used for otoliths before. I know of about 1, maybe 2 papers that use this method, so what we're doing is very much a proof of concept here. It's called SIMS, or secondary ion mass spectrometry, and the great thing about this is it's much more precise. Whereas the trace elements in strontium, the laser spot is about 50 microns across, this is either 5 or 15, depending on how accurate you want to get, so you can get really fine resolution data, almost like a week or even a couple of days of the fish's life history, where instead of the sort of month that you might be grabbing in the other methods. And also, luckily, that also comes with an added precision in the quality of the actual oxygen isotope measurements. The downside with it is it's a lot slower, whereas I can do sort of 50 samples of the trace elements in an afternoon. This, I can manage like 3 or 4 otoliths. So that's one of the reasons why we're doing this as a pilot study, to see whether it's worthwhile doing before I go and prepare, a huge heap of focus and spend an awful lot of time and money in the lab. We want to know that it's going to be effective first. So this is just a summary of what I've done so far. I've basically prepared a load of otoliths, sent them through, prepared another lot, sent them through, and then prepared another lot. The trace element analysis we have actually all completed. I'm just waiting to get the final results from the lab, which should be coming this week. The strontium isotopes, we had a little bit of an issue with the fact that we couldn't do it over here in Western Australia, send it over to a lab on the East Coast, and their machine broke down. So I'm having to wait for that to get fixed. And then the SIMS, as I say, we've done, and I'm just working out how to analyse that data. So my data analysis is pretty straightforward. I'm looking at margin analysis first. We know where the fish are from, so the first thing to do is see whether we can actually see any of those differences in the chemistry. And then I'll also do the same sort of analysis but on the core data to see if we can see any differences in spawning populations. And then once I've got that data, if we've actually got positive results, then we can go through and compare what we've found with the genetics results. Once all that's done, we can do a bit of a deeper dive, and we can look at the transect, so that from their core to the margin, we can actually see how the elements change, see if we can match that up with movement. And then once we've got that data for the individual fish, we can then combine it with relatives and see whether we've got any sort of tracking movement to suggest that the fish are maybe coming together at one point, even if they're then separating out. So that's what we're hoping to do. I've got some very preliminary results. These were done on Friday, so don't take them with a very big pinch of salt. But so far it's looking quite positive. This is Janus carpentatus. As I say, this is actually half the fish that we've sampled. This is about 60 fish. But we're already seeing a nice north-south divide. It may not look that impressive on the PCA, but what we found was that it's actually the first 4 dimensions which are all contributing to that, and unfortunately I can't display 4 dimensions. But the per manivore values should hopefully convince you that what we're seeing is real. Millerite is a little bit less exciting, but you've got to remember that that's all from the south. We do have these outliers, and my next task is to work out if that's just screwed up data or whether there's something biological going on. And when we remove those outliers, we can see that there is some stuff going on, but it needs more exploratory work done to see if there's anything actually interesting there. So my future work is really more of the same. We are going to try and get those northern P mineral processed and samples so we can see if we've got a similar north-south divide going on, try and work out what these anomalies mean, get more data in there for the Janus and see whether we've got anything that's driving that north-south divide. We also did a cap analysis on Friday, and there was some misclassification of the fish. Not many, but a few. And I really want to see whether that is just screwed up data again, or whether that's evidence of possible movement between north and south. And then also just to try and see whether this SIMS method is a useful method for the otoliths, because if it is, then that would be pretty cool. So that's it. This is obviously, although I'm the one who's done most of the sort of preparation, I could not have done any of it without help of so many people. Science really is collaborative. So thank you.